Okay, Sarah Redskins, we're here to talk about volume, specifically the disk method for today. And it's kind of interesting why they call this the disk method. But first, just a quick review of volume. All right, so let's suppose I have here just say like a soup can or something, sideways soup can. All right, so I could define this by its radius and its height. And we have a volume formula for this. It's the area of the base times the height for any right solid, but specifically for this cylinder, the area of the base would be pi times the radius squared times the height of that solid. All right, now let's imagine that we take a cross section. Let's take a cross section of this. And when I pull that out, that is going to be, well, it's going to look like a little disc. All right, so here's my pullout. I pop this out, and it's a little disc. And it's going to have the same radius, okay? And I could calculate the volume of this the same way, pi r squared h. But let's now pop out another little disc. Okay, good drawing, huh? So here's another little disc. Same radius and a height, like a shorter height, but the same thing. We'd say, okay, pi r squared h. So imagine that I cut this tube up here. Let me switch to blue. If I cut this whole tube into an infinite number of discs, infinite discs, and added them all up, would I not get the volume here? And adding up a whole bunch of infinite discs is kind of like, oh, hey, we have something in calculus that does that adds up incrementally from A to B, a whole bunch of disks. And here's where the formula for this comes from. Let's come over here. Oops, I drew right in the middle. So let's consider a garden variety function, right? Looks like this. Here's my function. And the disk method is used to rotate solids. So you'll see these arrows down here. Maybe I should make that a different color. Let's make it white. But you see these down here. And so let's imagine that here's my A and here's my B. So I'm going to take this section of the curve and rotate it all the way around the x-axis. So it looks something like this. And the reason they call this the disk method is because what is my radius of each one of these infinitesimally small disks? Well, my radius happens to be f of x. I guess I'll make that all white. In our textbook, they call it r of x for radius. So let's see. If I multiplied the radius squared times the height of the solid. Now, what is the height of each one of these disks? Well, the height of each one of these disks is my dx, the difference in x. So there's my dx. And I want to add up an infinite number of these little disks from A to B. And this ends up being my formula. This is the formula to, oops, I forgot my pi though, pi r squared. So this ends up being our formula. Volume equals pi r squared. This is one of the most common things I forget to do is square this. But it's r squared. And because pi is a constant, we write it out in front of this. And this, my friends, is the formula to figure out the volume. Whoops, don't forget your endpoints. This is the formula. It looks more like this over here. This is the formula to figure out the volume of a revolution around the horizontal axis. All right, so here's an example of what's going on here. We're going to find the volume of a solid formed by revolving the region bounded, got to proofread better, bounded by f of x equals the square root of sine of x. So when I graph this, and I'm kind of cheating, I'm looking in the book. If you're on page 448 in the book, this is positive 1, this is negative 1. This graphs something like this. And what we're doing is revolving this around the x-axis. Hold on, I'm going to do that different color. Revolving that around the x-axis. So it's like a little squirrely arrow. Some people, I guess, draw them the other way. Okay, but anyway, this indicates which axis, because in a minute we're going to do this. Or maybe we'll save that for tomorrow. But anyway, you can revolve around either axis. And by the way, you won't necessarily get the same volume. If I revolve this around the y-axis, I'm not going to get the same volume as if I revolve it around the x-axis, because it's going to be a different shape. So anyway, when I revolve this around the x-axis, it ends up kind of looking like an egg structure. So what we want to do is we want to find a disk here. Here's my delta x. So I want to find a disk here that I can, rotate around the x-axis and turn it into, add them all up and turn it into my volume. So here's my volume formula. Pi times the radius from A to B of capital R of x. The R just stands for radius. Squared, don't forget the square of the radius, times the dx. That's the height of each one of these disks. Okay? So if R of x, we'll let R of x equal f of x, which was the square root of the sine of x. So we're going to revolve this. Now this is also another trick too. A lot of times there's a tendency to want to, straight out of the gate here, start with my antiderivatives, but we first want to plug it into my formula. So we'll plug it into the formula. And when I put this into my graphing calculator, by the way, my A is 0, and my B up here ends up being pi. So we're going to have a 0 to pi. And as you can imagine, this 0 is going to be helpful, come in handy. And let's see. Do you see now why this first example picks the square root of x? Because when I square it, it just becomes the sine of x. So I end up saying volume equals pi times the integral from 0 to pi of sine of x dx. Now, this is one of the reasons why it made it a little bit easier. This ends up equaling pi. All right. The inverse, or I'm sorry, the antiderivative of sine is negative the cosine of x. And that's going from 0 to pi. So, let's keep on going. I have pi times the opposite, the cosine of pi, minus, okay, maybe throw in a little parenthesis here, minus the opposite of the cosine of 0. So the sine of pi is -1. So I have a negative here. The cosine of pi is a -1. So I changed colors to show that that was different. Minus, so this minus gets us a minus here. And the opposite of the cosine of 0. Well, the cosine of 0 is 1. So the opposite is +1. Just trying to keep all of our signs straight here. So I end up with volume, whoops, I switched colors, that's okay though, pi times +1 plus 1, or 2 pi. And the answer, whatever the units are, but the answer is cubic units. But if you get the 2 pi, that's pretty good. So that's how this works. You have to first remember to square this, then you're taking antiderivatives of stuff. Okay? Next, let's take a look at an example using a line that is not a coordinate axis. So it was pretty easy when it was spinning around the x-axis, but what happens if I want to spin it around this axis, say y equals 1, g of x equals 1, and I have a function. So my radius would normally be, well, it would come down to here if I were spinning it around this axis, but I'm not. I'm spinning it around this axis. So what I want to do to figure out this radius, this is my r of x, is I'm going to take my f of x and subtract that g of x. Okay? So it's this f of x minus this g of x. So let's write that in. And then we can get started taking the integral. So f of x is 2 minus x squared. And we're subtracting g of x, which is just 1. So let's see if I simplify this. What do I get? 2 minus 1 is 1. So I'd have 1 minus x squared. All right. So now I can use my volume formula here. Pi times the radius of, I got to figure out my a and my b, but of r of x squared, radius squared, times the height. Now remember, the height is the width of this infinitesimally thin disk that is being revolved, and then we're just this interval symbol means add up all those tiny disks. All right, so the next thing we have to do is figure out, oops, I meant to point there. We have to figure out what this point is and what this point is. So those points both happen to be 1, or 1 away from the origin. So it's -1 on the left and -1 on the right. So, in our formula, we have pi times the integral from -1 to 1 of 1 minus x squared. Don't forget to square this. This is the most common mistake I see students make. I make it myself oftentimes. If we were standing at the board in the classroom, you'd probably see me do this at least once. Forget to square that. So, here we go. I'm not going to use substitution because this is a pretty simple one to expand. It just becomes 1 minus -1, -1, -2x squared plus x to the 4th, right? I just FOILed that. And multiply it by the dx. Now we can use calculus to solve the rest of this. So the volume equals pi times, let's take the antiderivative, that becomes x minus 2/3 x cubed, and let's see, plus 1/5 x to the 5th. And remember, we're done writing plus c because we know they always add off. All right, so what this means to do is to multiply pi times this whole expression with the 1 substituted minus this whole expression with the -1 substituted. So I'm not going to do all that arithmetic for you. I'll let you type it into your calculator. But this ends up being 16/15. Okay, which is 16 pi divided by 15. So notice when you have the pi in the fraction and you're not using a decimal approximation, this ends up being an exact answer. Yay! All right, so that takes care of the disk method. Tomorrow, Monday, I guess, we'll look at the washer method, and it's very, very similar to the disk method. So they're related. In fact, that's why they're both in the same section of the book. But for now, have a great Redskin day and enjoy your weekend.